Okay, so in this video, before we get into introducing a whole lot of new graph shapes, although we do now look at some of these graph shapes in the latter part of Year 10, so some of them should be familiar, but I'm going to treat these lessons as if you haven't ever seen this before. So before we get into introducing the hyperbola, the truncus, the square root graph, circles, semicircles, etc., I want to talk generally about our growing understanding of transformations of graphs. So we want to start to formalize it a little bit so that we can understand every time we introduce a new graph shape, we start with that basic shape, and then it's our understanding of transformations that enables us to sketch variations of that shape. And we want to see how the transformations that we've gradually been observing through graphs over the last couple of years are actually exactly the same for all functions. And if we can see those commonalities about them, we'll be able to then apply them to new functions, and perhaps functions that we don't even know what the equation is. So the first kind of transformation I want to look at is the dilation from the x-axis. And I've given these examples showing how it applies to the linear graph, the quadratic graph, and the cubic graph. Now, you might not be super familiar with the shape of the cubic graph. You would only have met it for the first time last year, and we'll review cubic and quartic functions later on in the semester. But I want to take these three different shapes. The linear graph becomes a bit trivial, and it's sometimes hard to see the different patterns because it's such a simple graph shape. The parabola shows us lots of things, but it is lacking in a few areas, and the cubic also shows us other things. We will introduce some graphs down the track. The square root graph in particular is the first graph shape we introduce, where we will need to consider some additional transformations. But for now, for the graphs we're going to introduce in this topic, we're going to focus on dilation from the x-axis, reflection in the x-axis, and translations left and right and up and down. Okay, so it's important that we also start to develop the right language. So we don't talk about stretching and squashing graphs. We use the proper term dilation. Okay, and when you dilate a graph, you're going to need two bits of information. You're going to need to know two bits of information. That is, you're going to need to know how much do you want to dilate the graph by, what is the scale factor, and in which direction do you want to dilate the graph. So in this case, we are looking at dilating from the x-axis. So if that's my x-axis, we're going to be looking at stretching away from that axis. Okay, and that's what's really important too. Sometimes when students initially learn about sketching parabolas, here I've got the graph of y equals x squared and the graph of y equals 2x squared, and some students think about this as being making, as you change this number, you make the graph thinner. Now the graph does get thinner, but it's misleading in terms of actually connecting to what is that 2 in front of the x squared actually doing. And what it's actually doing is making the graph taller. Okay, it's stretching it in this direction. We're multiplying all of the y values by 2 to get a taller and hence thinner graph. So that point that was at -1, 1 is now at -1, 2. This point that was at -2, 4 is now at -2, 8. This point that was at -3, 9 is now at -3, 18. Okay, so we're doubling all the y values. The same happens with the cubic. If we take y equals x cubed as this blue graph, y equals 2 times x cubed as this red graph, the difference between the two is that we've doubled all of the y values. We've stretched away from the x-axis by a factor of 2 to get the red graph. Okay, the same is true of the linear graph, although as I said it's a bit more trivial because we think about this as gradient, but it is, a dilation is going to change the gradient. If you have y equals x and you then draw y equals 2 times x, you are going to be dilating the graph away from the x-axis by a factor of 2. You are doubling all of the y coordinates to create a steeper graph. So this pattern applies to all functions. Okay, so we can talk more generally about 2 times f of x. If we take the graph of y equals f of x and dilate it by a factor of 2 from the x-axis, its equation will be y equals 2 times f of x. So we saw that happen here. We've got y equals x. If f of x is x, 2 times f of x is 2x. If f of x is x squared, then 2 times f of x is 2 times x squared. If f of x is x cubed, then 2 times f of x is 2 times x cubed. So any function if you stick a 2 in front of it, you are dilating it by a factor of 2 from the x-axis. We can obviously extend that to other graph types. So let me just pause the video a moment while I just expand out the CAS so we can see what's happening over here in a bit more detail, and then we'll go on talking about the next transformation. Okay, so here we are seeing, I've enlarged the side screen so that you can actually see what's on the screen a little better. So I've defined a function, f of x, which is x squared, the parabola. Okay, now we're going to focus on looking at a times f of x. Okay, so this, I can't write over here, but this function here, and how that is different from f of x. So I've got a slider down here where at the moment a is equal to 1. So at the moment these are the same graph. F of x and 1 times f of x is the same thing. If I increase the value of a, based on what we've just talked about, we expect the graph to get taller and thinner because we're multiplying the y coordinates by that value. So this is 1.2 times x squared. This is 1.4 times x squared, 1.6 times x squared, 1.8 times x squared. There's 2 times x squared, which was the graph we just looked at on the screen. All of the y coordinates have been doubled. Okay? And we can continue to make a bigger and it will make the graph taller and thinner. If we were to look at what happens when a is smaller than 1 but still bigger than 0, so a equals 0.8 here, what we've done is we've multiplied all of the y values on that graph by 0.8. So the graph ends up getting squashed because you're making the y values smaller when you multiply it by a number smaller than 1. So that's 0.6 times x squared, or 0.6 times f of x, 0.4 times x squared, 0.2 times x squared, and then if I let a equal 0, we just don't have a quadratic function at all, we just have the line y equals 0. We'll talk about the negatives in a minute. So we're looking at a being a dilation from the x-axis. Now it doesn't just have to be a quadratic. Let's go over here again and redefine our function. Let's change it from being f of x to being, let's just make it x for now, the linear graph. Okay. So now when I go back over here, I'm going to see I've got y equals f of x is drawn, it's black, it's underneath the blue line. Y equals a times f of x, and as I make a bigger, we're multiplying the y values. Sorry, we're multiplying, I'm just going to actually move the slider up out of the way of the graph. We're multiplying the y values by, in this case, 1.6, and so we get a steeper graph every time we do that. Okay. Again, if we were to multiply the y values by a value less than 1, it's going to squash it. 0.8 times x, 0.6 times x, 0.4 times x, 0.2 times x, 0 times x is just a horizontal line. We'll talk about the negatives in a bit. Okay, so as I said, the linear graph is pretty straightforward. Let's change the function again. Let's redefine the function now as being x cubed. And we'll go back over here. And again, as we make, now a is 1, so they're the same graph. As we make a bigger, the graph gets stretched away from the x-axis, so it becomes taller and thinner. Okay. As a gets less than 1, so the graph will get wider and flatter because we're multiplying all of the y values by 0.4. We're dilating the graph by a factor of, in this case, 0.2 from the x-axis. So that's going to squash it down. Okay, but it's all about that vertical stretch away from the x-axis, and you're stretching by a factor of a. Okay, let's change the graph to a graph shape we might not be so familiar with, or let's make it something a bit more complex. So let's maybe make it x squared plus x, for example. Still a cubic, but let's have a look at what that looks like. Okay, sorry, let me make a back to 1. Actually, x squared plus x is a bit boring. Let me make it something else. It's a bit of a different shape. Let me make it x cubed plus x squared. I'm sorry, can't edit it there. Hold on. Let's make it that. Okay, and let's have a look now. Actually, I might go with a bigger one. Hold on. Sorry. Let's go back over to here. Let's make it x cubed plus, just so we can see what's happening a bit more, let's make that 3x squared. Okay, so now we have the black graph, which is underneath, is f of x. The blue graph on top is a times f of x. As we make a bigger, that dilates the graph away from the x-axis. So you see when it's above the x-axis, that means it gets higher, okay, but when it's below the x-axis, when you're stretching away from the x-axis, the graph gets lower, okay. So the graph is stretched away from the x-axis. If a was less than 1, it would squash down towards the x-axis, okay. So that applies to all graphs. You take a function f of x, I give you a picture of what it looks like, and I ask you to sketch 2 times f of x. You dilate all of the points by a factor of 2 from the x-axis, that is, you double all of their y coordinates. Okay, let's go back over to the notes for a moment. Alright, so let's now talk about the second type of transformation we want to look at here, which is reflection in the x-axis. So when the whole function is multiplied by -1. So here we see we've got, oh sorry, let me get my CAS back. Here we see we've got y equals x up here, and when we multiply x by -1, we get y equals -x, and the whole graph gets reflected in the x-axis. Okay. Here, when we've got the graph of y equals x squared, and we multiply x squared by -1 to get y equals -x squared, same thing happens. The whole graph is reflected in the x-axis. Okay. When we have the graph of y equals x cubed and we multiply it by -1, so we get y equals -x cubed, the same thing is happening. The whole graph is reflected in the x-axis. Okay. And so we get the blue shape instead of the red shape. So again, we can generalize that to any function. If we have y equals f of x, and we then draw y equals -f of x, that is a reflection of that original graph in the x-axis. When we reflect in the x-axis, we're multiplying all of the y coordinates by -1. Okay, so let me go back to my CAS and let's have a play around with that. Okay, I'm going to stick with this more complicated shape because we've just looked at simple diagrams of y equals x squared, and y equals x cubed, and what happens when we make a negative. So if we were to here now make a negative, so I'm going to have to go step at a time. So if we decrease the value of a, obviously when a equals 0 we've got no function at all, so there's no point in that. But if a is a negative value, let me just make it -1, we can see we have the original graph reflected in the x-axis. Okay. If a is negative something else, so let's make it, -2, for example, there's actually 2 transformations happening there. We have dilated the graph by a factor of 2, that's the 2 part of the number, and the negative has reflected in the x-axis. So it is both stretched away from the x-axis by a factor of 2 and reflected in the x-axis. There's actually 2 transformations happening if we have -2 times f of x. The negative, the reflection, and the 2 is the dilation by a factor of 2. Okay, let's go back to the notes. Okay, now let's talk about translations. So translating a graph up or down. So when a number is added to or subtracted from the whole function, the graph is translated up or down. This means that a certain amount has been added to or subtracted from the y coordinate of each point of the graph. So again, if we have y equals x, and then we compare that to y equals x plus 5, that x plus 5 is the whole graph translated up by 5. So we're taking every single y coordinate and adding 5 onto it to get our new graph 5 higher up. Again, if we have y equals x squared and then we add 5 onto the end of that, so y equals x squared plus 5, we're taking that whole original graph and translating it up by 5. Okay, same with the cubic. If we have y equals x cubed, sorry, it looks like that x-axis has got quite faint in the printout, so that's the x-axis there. We're taking and we then draw the graph of, so the blue graph is y equals x cubed, the red graph is y equals x cubed plus 5, so that is taking that whole original graph and translating it up by 5 units. We're adding 5, okay? So the whole graph translates up by 5 and we get our new shape. And again, we can generalize that to any graph. If we have the graph of y equals f of x, doesn't matter what the equation of it is, if we then try and draw the graph of f of x plus 5, it's going to be that original graph translated up by 5. Okay, let's go back across to the CAS. Okay, so I've actually gone back to defining the function as y equals x squared in the CAS, just while we deal with this. So I've got the graph of y equals x squared is the black graph, y equals f of x, which is underneath the green graph. And then I've got the graph of f of x plus k, which is the green graph, and at the moment k is 0, so they're the same graph. So as we increase the value of k, we see the whole graph shape translating up. Okay. If we decrease the value of k, the whole graph shape translates down. So we've simply subtracted 5 from all the y values. There's no change to the shape, it is just moving up and down. Okay. So let me just change the function again. It's going to get a bit messy here because I've got to scroll across a number of screens. Okay, so if we now were to have a look at the cubic, no, let's go to the linear function, f of x equals x, and if I go to find f of x equals x and go back across to this one, okay, so at the moment k is 0. As we increase the value of k, we are translating the graph up. As we decrease the value of k, we are translating the graph down. If we change the function to the cubic, sorry, let's go back here, y equals x cubed, okay, and back across to our vertical translations. At the moment k is 0, so it's not translated up or down. If we increase k, we take this cubic shape and translate it up. If we decrease k, we take the cubic shape and translate it down. And that is true for any function. So if we again make it that slightly different cubic, this one here, and have a look at that, go back across to the vertical translations. At the moment k is 0, so the green graph hasn't been translated up or down at all, but if we take this function f of x, which is the black function, and add k, where k is 1, that whole shape is just translated up by 1. So that is, you've added, or in this case where I am now, k is 3, so up by 3. We've added 3 onto all of the y values. Let me just give you a grid. Sorry, I did mean to add on the grid before I started, just so that you can see exactly that each of those points is 3 higher than it was. Okay. Similarly, if k is negative 2, that is f of x minus 2, we're taking the graph of f of x and translating it down by 2. Okay. Alright, let's go back over to the notes and talk about the final transformation for this video. There are 2 transformations we're ignoring for now, and that is the dilation from the y-axis and the reflection in the y-axis, and that's because for now we don't need it as a separate transformation. All the functions we're dealing with, if you take a parabola and reflect it in the y-axis, it's still the same graph. If you take a cubic and you reflect it in the y-axis, it's the same as if you had reflected in the x-axis. So we don't need to think about those new transformations just yet. We'll introduce those when we get to a graph type where they become important. Let's just get on top of these. So dilation from the x-axis, reflection in the x-axis, translation up and down, and we're going to finish off by having a look at translation left and right. Okay, so translating left and right. So when a number is added to or subtracted from the x part of the function, so inside the function, okay, then we translate left or right. And this is a bit tricky. You actually have to interpret it backwards to how it appears in the function. So for example, here, let's look at the quadratic first. We've got y equals x squared and y equals x minus 3 all squared. And that graph, even though we're minusing 3, hasn't gone left by 3, it's actually gone to the right by 3. Apologies there, the axes have got a bit faint again. That's the y-axis there and the x-axis there. So we've gone to the right by 3 when we did x minus 3 all squared. We see the same thing happened with the cubic. We start with y equals x cubed, we replace the x with x minus 3, okay? So that is, we go from this being y equals f of x to this being y equals f of x minus 3. So it's just the x that gets replaced by x minus 3, still inside the cubed function. The graph translates to the right by 3 again, okay? So minusing 3 inside the function means right by 3. Similarly with the line, again we've lost our x-axis there, sorry, that's the x-axis there. If we have y equals x and we replace the x with x minus 3, we go to the right by 3. Now in the case of the linear function, if your original function is f of x, then f of x minus 3, sorry, if your original function is f of x equals x, then f of x minus 3 means replacing the x's with x minus 3, so you just get x minus 3. And actually, that's the same as, for the linear function, doing f of x take away 3. So actually what we're seeing here is translating right by 3 is the same as translating down by 3 for the linear function. That's not true for the other two though. If we could think about that as going down by 3, but we can also think about it as going to the right by 3. And that's why the linear function is a bit of an awkward one to look at with transformations, because it's such a simple shape that actually translating left and right isn't really very different to translating up or down. Okay, the key thing though with the translations left and right is it's the opposite of what you think it should be. Okay, so if for example we had y equals, so we've seen that f of x minus 3 is a translation to the right by 3. If we had y equals f of x plus 2, that would be a translation to the left by 2. Okay, if we had y equals f of x minus 7, we would be going right 7. If we had y equals f of x plus 8, we would be going left by 8. Okay, so it is the opposite, and that's something to do with the fact that it's inside of the function, whereas all the other things we've looked at up until now, we've had f of x, when we dilate it from the x-axis, we multiply the whole thing by a. When we reflect it, we multiply the whole thing by -1. When we translate it up or down, we add on to the whole thing. This is the first time we've inserted something in here, and it turns out to be kind of the opposite of what we might expect it to be. So let me just go back over to the CAS and let's have an explore of that, and then let's work through some examples. Okay, so again I've gone back to the parabola. So f of x is defined as y equals x squared. That's the black graph. Underneath the black graph I've got a pink graph, which is f of x plus h. Okay, so I've got a slider here for h. I can alter h. So as I make h bigger, so here you see I've got h equals 1. So that's the equation of f of x plus 1, and it's gone to the left by 1. F of x plus 2 goes to the left by 2. F of x plus 3 goes to the left by 3, etc. Okay. If we make h negative, so if h were to be -1, the equation now is f of x plus -1, which is f of x minus 1. And we can see the graph has gone to the right by 1. F of x minus 2, the graph goes to the right by 2. F of x minus 3, and the graph goes to the right by 3. Okay, so we can see that happening for the parabola. Let me alter the function again. So now let's make it the cubic. Okay, let's go back across to 4. Here we are. Okay, so again, cubic shape. If we make h bigger, the graph translates to the left. So f of x minus 4 all cubed is the graph of f of x translated to the left by 4. If we make h negative, that is we subtract something inside the function. So now we have f of x minus 2, which is in this case x minus 2 all cubed. The graph has gone to the right by 2. Okay. If we have a look at that more complex function, this is still a cubic, that looks more complicated. Here is both functions when h is 0, so no translation to the left or right. If I make h bigger, the graph translates to the left by, in this case, 3 units. So every point has been translated across to the left by 3 units, and we've got our pink graph sitting over here. Okay, if we make h negative, so h is -1, this is f of x minus 1, the graph translates to the right. Okay, so we want to start to generalize these ideas of the transformations. We can then compile them all together. Okay, so we can now have a look at, oh sorry, let me make a back to 1. Oh. Let's start at the beginning. So if a is 1, oops, and h is 0 and k is 0. Okay, so there's our function f of x. If we increase a, we're dilating it away from the x-axis. If we increase h, we're moving it to the left. If we increase k, we're moving it up, and we can combine all those things together. Okay, so this is the graph of, let me just make them whole numbers. This is the original function dilated by a factor of 2 from the x-axis, so that's why its shape is taller and thinner, and then translated to the left by 1 unit. So everything's gone to the left by 1 unit. You can see that minimum turning point is now at -1 instead of being at 0, and the graph has been translated up by by 2 units. Okay, so all of those things combined together are going to look like this: a times f of x plus h minus k. And this is essentially what we're working with when we're working with turning point form, but we want to generalize that out from just being about quadratics and cubics and be able to think of other functions. Okay, let's go back to the notes and work through some examples. Okay, so summary of our transformations. If we have a number, let me make CAS back. If we have a number times f of x, we are taking f of x and dilating it by a factor of a from the x-axis. If we have a negative at the front of f of x, so negative 1 times f of x, the graph of f of x has been reflected in the x-axis. We should note here that if we were to, for example, have negative 2 times f of x, that would be the reflection in the x-axis, and that would be the dilation by 2 from the x-axis. Okay, so there's two things happening if a is a negative value other than 1. F of x minus h, the graph is translated to the right by h. Okay, so just a bit of a cautionary tale there. X minus h is to the right by h. Okay, x plus h is to the left by h. Whereas the f of x plus k is much more intuitive. Adding on k translates the graph up, and subtracting k translates the graph down. So it is this one that we just want to be a bit cautious about. As I said, we'll add in dilation from the y-axis and reflection in the y-axis when that becomes necessary with our functions down the track. Okay, let's have a look at an example. In each of the following, the graph of y equals f of x is shown. It doesn't matter what the equation of f of x is, that's not the point. We want to take this original graph and use that and our knowledge of transformations to sketch the graph of y equals 3 times f of x. Okay, so 3 times f of x is a dilation by a factor of 3 from the x-axis. So all of the y coordinates are getting tripled. So this point that is at 1, 4, the y coordinate gets tripled and it's now at 1, 12. This point that's at 3, 0, its y coordinate gets tripled and it's still at 3, 0. 0 times 3 is still 3. It's still 0, sorry. And same with this point. Tripling this y value will still leave it at 0. You can pick another couple of points here. It looks like we go through this point here at 4, 6. Tripling 6 would be right up to 18, so it's going to be much higher up there. This is roughly 2, 2, so tripling 2 takes us to 6, so it's going to be just a bit more than 6. And we've got some symmetry happening over here. It's going to be a bit more than 6 up here. That's not going through a nice exact point. Sorry, let's go with this one. 0, 9 on 4. 9 on 4 times 3 is 27 on 4. 27 on 4 is 6 1/4, so just a bit more than 6. So that's the nice symmetrical point with that one. Again, this point's going to come way off the charts up here, so it's going to be nice and tall and steep. It's going to turn at that point. It's going to cut through there and turn at that point. It's going to go through there and turn there, and then be steep heading off up to here. Okay. So it is a, let me just, sorry, just wanted to make that a bit steeper at the end there. It was a bit too close. Okay, so the graph is dilated by a factor of 3 from the x-axis. We want to take the same graph and this time sketch the graph of y equals negative f of x, which is a reflection in the x-axis. So that point at 1, 4 now goes to 1, negative 4. The point at 1, 0. So when we reflect in the x-axis, we're multiplying the y values by negative 1. So the x-intercepts aren't going to move anywhere. And again, we can take some points. So that's 0, 9 on 4. So 9 on 4 is just 2 1/4. Is going to come down to 0, negative 9 on 4. We've got the same point over here. It's going to mirror down to here. We can pick another point. It looks like we go through about negative 2, 6. So we're going to go through negative 2, negative 6. Looks like we go through about 4, 6. And so we're going to go through 4, negative 6. And you might just want to take that point right on the edge and plot that in the same kind of place down here. So we've got x-intercept. There's no reason not to be precise when you have a grid. In fact, a grid demands more precision of you than not. So making sure that you are nice and precise about what's happening. Okay. Sketch the graph of -2 times f of x. Okay, so we've got two things happening there. Okay, we've got the reflection in x, plus we've also got a dilation by 2 from the x-axis. Okay, so we're combining together the two things that we just did, although, no, sorry, we dilated by 3 up here. So we're going to double the y value. It's going to come up to 1/8. That's the dilation by a factor of 2. And then when we also reflect that, it's going to come down here to 1 -8. Okay. This point, when we reflect in the x-axis, stays here, and when we dilate it from the x-axis by a factor of 2, still stays here. The two x-intercepts will both stay where they are. We can pick some other points. So 9 on 4, when we double that, that's 9 on 2, which is 4.5. Okay, and reflecting that in the y-axis, it comes down to -4.5. And we've got the nice symmetric point over here at 2, so that's going to be at 2 -4.5. And then we might take this point that looks like it's at about 4.6, doubling that is 4.12, and reflecting that it's at 4 -12. And the same here, -2.6, doubling the y value is -2.12, reflecting in the y-axis is going to take it down to here. So it's both taller and thinner because of the dilation by a factor of 2, but it is also upside down because of the reflection in the x-axis. Then we want to sketch this graph here. So we've got f of x minus 2, so that's a translation, so subtracting 2 from the whole function, translation 2 down. So we're going to take each point and move it down by 2. So 1, 4 goes to 1, 2, 3, 0 goes to 3, -2, -1, 0 goes to -1, -2, 0, 9 on 4. 9 on 4 is 2 1/4, so it's going to go down to 1/4. Okay, same symmetric point over here. This point at 4, 6 is coming down to 4, 4. -2, 6 is coming down to -2, 4, etc. We can draw in our graph shape. So we're not asking you to come up with the equation for this graph. We're not asking you to calculate x and y intercepts. You won't always know where they are. It just happened the x-intercepts were still in the same place in these previous ones. Here we actually don't have a way to calculate those x-intercepts. It's not about that. It's about you understanding the transformations and being able to actually execute that with the graph. Okay, E, we want to sketch the graph of f of x minus 2. Okay, so when it's inside the function, that's the translation left or right, and we remember that it's sort of backwards to what we think, so if we're subtracting 2, we're actually going to the right. So this is a translation to the right by 2 units, so we're going to take each point and move it to the right by 2 units. Okay, so 1, 4 goes to 3, 4, 3, 0 goes to 5, 0, -1, 0 goes to 1, 0, 0, 9 on 4 goes to 2, 9 on 4, 2, 9 on 4 goes to 4, 9 on 4, this 4, 6 goes to 6, 6, -2, 6 goes to 0, 6, and you can plot a few more things across by 2 units if you want. Can we just pass there? So to help you get the shape right. And there is our graph translated to the right by 2. And then we can combine all of those things together. Okay, so this, we have a dilation by 2 from the x-axis, so it's going to be taller and thinner. This is going to translate the graph to the left, plus 1 will go to the left by 1. This is going to translate the graph up by 3. So we're going to take each point, we're going to stretch it away from the x-axis by a factor of 2. So in the case of 1, 4, it goes to 1, 8. Then we're going to translate it to the left by 1, so it comes across to here, and up by 3, so we finish up there. Okay, and we want to do that for a number of key points. Dilating the x-intercept at 3, 0 won't do anything. Translating it to the left by 1 and up by 3, we're going to finish up there. That's the turning point. -1, 0, the dilation doesn't do anything, left by 1 and up by 3, that's that turning point there. Okay. 9 on 4 becomes 9 on 2 when we dilate it from the x-axis by a factor of 2, left by 1 and up by 1, 2, 3, so it's going to come up to here. Alright, we'll have a nice symmetric point over there. Let's maybe take this point at -2, 6, it goes to -2, 12 when we dilate from the x-axis by a factor of 2, left by 1 and up by 3, it's going to end up here off the graph, but it just gives us somewhere to aim at, okay? This point here, also at 4, 6, goes to 4, 12 when we dilated it, and then left by 1 and up by 3 is going to also be up here. So it's taller and thinner. It's also been moved or translated to the left and up. Okay, let's have a look at these. If we have a function g of x, we want to describe the transformation or transformations that map y equals g of x to y equals 5 times g of x. Okay, so multiplying the whole function by 5 is a dilation by factor of 5 from the x-axis. Let's not get lazy. When we're talking about dilations, you need to use the word dilation. There needs to be what factor are you dilating by and in which direction are you dilating. To get from y equals g of x to y equals g of x plus 8, okay, so plus 8 inside the function is a translation left or right, and it's the opposite. So again, we're going to use the word translation. We want to formalize our language. Translation, if we're adding in there, we're going to the left. So translation left by 8 units. Okay, so again, we need to identify that it's a translation, the direction that we're going, and by how much. Okay. If y equals g of x take away 3, okay, so this minus 3 here, outside of the function is a translation down by 3. Translation down by 3 units. Again, identify that it's a translation, which direction you're going in, and by how much. Alright, here we've got y equals negative 1/2 times g of x. So there's two things happening there. The negative means that we have a reflection in the x-axis, and the 1/2 out the front means that we have dilated, so we're doing dilation by factor 1/2 from the x-axis. So the graph's going to get flipped upside down and squashed in closer to the x-axis because we've got a dilation factor that's less than 1. Here we have two things again, okay? So let's be clear about that. This negative was this reflection, and this half is this dilation. In this graph, we've got a 3 out the front, 3 times g of, and then a minus 2 inside the function. So that's a translation left or right. So the 3 out the front is a dilation by factor 3 from the x-axis. So we're stretching it away from the x-axis by a factor of 3. We're multiplying all the x-coordinates by 3. So that's the yellow transformation. And then the blue, the negative 2 inside the function, subtracting 2 from x, is a translation. It's a left or right translation, and because we're subtracting, it's to the right. So translation right by 2 units. Okay, again, here we've got two transformations. We've got a negative out the front here, and we've got a plus 6 here. So the negative out the front is we've multiplied the whole thing by negative 1, so that's our reflection in the x-axis. And then the plus 6 is outside of the function, so that's an up and down translation. So it is a translation up by 6 units. Okay, we'll talk a bit more further down the track, really more formally next year, about the order of the transformations. You need to be careful about the order that you list these things in. Generally speaking, in terms of how we're going to be looking at the functions this year, we'll nearly always be listing the reflections and dilations first in whatever order you feel like, and then the translations come last. Okay, so that's quite important. It's possible to list it in a different order, but in fact, in this case, to list it the other way around, we would have to think about this function as being negative g of x take away 6. So you go down by 6 before you then do the reflection. So it's not just a case of you can't just take these two sentences and reverse them. That produces something different. You actually have to think carefully about it. So as I said, the format that I will be giving you the functions in for this year will nearly always, I'll let you know if it's different, but we'll certainly nearly always assume that it is reflections and dilations followed by translations. If your equation is in this form, a times f of x plus or minus h and then plus or minus k, this turning point form, it is always this dilation and reflection, then these translations. Okay. Alright, nearly finished. Third example and final example. Write down the new equation if the following translations are applied to the graph with the equation y equals root x. Okay, so if we think about f of x is the square root of x. Now, a dilation by 7 from the x-axis is 7 times f of x, which means that that is 7 times the square root of x for this particular function. You've multiplied f of x by 7, so you multiply f of x by 7. Okay? So that means, sorry, to go back to my black pen, so that means that the rule is y equals 7 root x. If we take y equals root x and we translate it up by 1 unit, we know that that is when we add 1 onto f of x. So if we add 1 onto f of x, we get root x plus 1. Okay, so that means our rule is y equals root x plus 1. So the 1's not under the square root, that's a left or right translation. We're adding it on after the function. Okay. Reflection in the x-axis, we know that is negative f of x, which in this case means if we have negative f of x, we have negative root x, and so our rule is y equals negative square root of x would be square root of x reflected in the x-axis, and then finally translating to the right by 3 units is f of x minus 3 if we're going to the right, and so that means in this case if we're replacing the x with x minus 3, we do the same thing in here and we're going to have the square root of x minus 3. So our rule is y equals square root of x minus 3. It's really important when you write square roots that you're really clear about where your square root ends. Don't be ambiguous about whether this does or doesn't include the plus 1. It doesn't in that instance, and be really clear about the fact that it does include the minus 3 in this instance. Okay, the work today is from a worksheet titled Transformations of Graphs.